in case people run into a few problems on this quick test, I thought I would do 2 of the questions for you, and that would give you a hint as to what was going on through the rest of it. To be able to do these 2 questions, I need 2 pages from the data booklet. The first one is page 17, where we've got standard entropy values for selected substances. And the other page I need is page 4 of your data booklet, because I'm going to be concentrating down here on this one. The first question I'm going to look at is question 5. This question states that the entropy change for this reaction during the formation of ammonia in the Haber process is given by this equation, and then we've got our delta S naught over here. Please note, entropy is always in joules, not kilojoules. Use the values in the data booklet to calculate a standard entropy for ammonia. So, how I would go about that. We've been given a delta S naught, and we've also been told that we're going to be looking in the data booklet. Now the data booklet only has delta S values, which would suggest that the equation we're going to be using, if we've been given a delta S naught, and we're going to be given delta S values for the reactants, and we need to find delta S for the products. So bearing that one in mind, we've got our delta S naught equals the sum of S naught of the products minus the sum of S naught over reactants. So this is the equation we're going to be using. Based on the question, we know that delta S naught is negative 99.5. And then if we have a look at these 2, our products is what we're trying to find. So we've got delta S naught, and this is NH3. It's the sum of them though. So when we solve this equation, we're going to get it for both NH3s, not just the one. And we've got the delta S naught, or the sum of our reactants. So our reactants, what we're looking for is 3 lots of H2 and an N2. Using the data from page 17, we'll be able to substitute this side in. Our 3 lots of H2 is 3 times 131, and our N2 is 192. So for completeness, I'll just finish this. Simplifying this, we've got minus 99.5 equaling the sum of sigma naught, S naught for our NH3s. And if we simplify all of this, we get minus 584. We can continue to simplify this. Which works out as 484.5. But what we need to remember is this, from our equation, is for 2 NH3s. So our NH3 would be 242.25. Now that we've reached our final answer, we need to have a look at significant figures. We were given 3 sig fig here as the only data in the question, which means we need to return to 3 sig fig. So our final answer will be 242 joules, not kilojoules, per Kelvin per mole. The next question I'm going to have a look at is question 9. So calcium carbonate present in limestone is stable under normal atmospheric conditions. When it's in a volcanic area and becomes very hot, it can thermally decompose. Given the information, use the second law of thermodynamics to show why limestone is stable at 25 degrees C, but not at 1500 degrees C. The second law of thermodynamics is the one about entropy, where for a reaction to be spontaneous, delta S must be positive. So what we're actually having a look at is we need to try and prove why at 25 degrees C, delta S is negative, but at 1500 degrees C, delta S is positive, and therefore the reaction would be feasible. Unfortunately, we don't have an equation that we can use for this one just now. We will be able to use a different one a little bit later on. So just now, what we're going to refer to is the equation that's here. And we're going to use this to work out the answer for this question. The two temperatures which were given, which we need to consider, are 25 degrees C and 1500 degrees C. But we don't use degrees C in these calculations. We need to convert these into Kelvin, so we need to remember that 0 degrees C is 273 Kelvin, so our 25 degrees C becomes 298 Kelvin, and our 1500 becomes 1773 Kelvin. Okay, so now using the equation that I just pointed out on that other page, for each of these we've got delta S of the surroundings equals negative delta H of the system over temperature, and we have that twice because we need to do the equation or two calculations. Okay, so having a look at the first one, delta H of the system given in the equation or given in the question is positive 178. So it's negative because we have to take this negative into account, but it's negative positive 178. But this is in kilojoules, and we can't have it in kilojoules because we're dealing with entropy, and entropy will be in joules. So as soon as we're given a kilojoules, we need to multiply by 1000 over the temperature, which is 298, and that all works out as negative 597.3. Same over here, delta H given in the question was positive 178. Again, it's a negative of that positive because of the negative sign here, and that 178 is kilojoules, so multiply by 1000. Our temperature is 1773, which when you pop that into a calculator comes out as negative 100.4. So that's us found delta S of the surroundings for each of those two temperatures. So using the equation that's halfway down page 120, which is the total entropy, equals the entropy in the system added to the entropy in the surroundings, we can substitute in our delta S for the surroundings for each of these temperatures into our equation. So this is going to go both directions because remember we're dealing with two temperatures. So for 25 degrees C, our delta S naught at 25 degrees C is equal to delta S naught in the system, which is given in the question on page 122 as positive 161. And we're going to add to that our delta S in surroundings, which is negative 597.3, which equals minus 436.4. If we go over to this side, our delta S naught at 1500 degrees C is the same for the system, is 161 plus our negative 100.4. And that popped into a calculator becomes 60.6. So if you have a look at the sign of these, delta S here is negative, but delta S here is positive. Therefore this reaction is not feasible, but this reaction is feasible because delta S must be positive for a reaction to occur spontaneously.